our solar-powered cooler project.
For our problem statement, we said that cooler users experience their ice melting in as little as 6 hours. Ideally, food and drinks would be kept cooled longer than this, and this is also a problem when dealing with food with non-waterproof packaging.
So while we were doing some research, we found some articles. One of our articles was about from the Health and Human Resources Department. It was about food safety, how you need to keep all your food in waterproof packaging in waterproof packaging. Our cooler, we wanted to eliminate that problem of the waterproof packaging, basically where you wouldn't have to have them at all. And then we also found an article from Prepared Pantry about ice melting too quickly and how keeping coolers out in the sun, how your food can spoil if not below 40 degrees. We want to make sure our cooler could actually solve that as well.
We also found an article from Yeti detailing ways that you can prep your cooler to keep it cold longer, such as pre-freezing your cooler. And we really just wanted to create a cooler that ideally had no prep, but still had that long time cold in the cooler. The cooler was first invented in 1951 by Richard Laramie. It was invented for storing and refrigerating food portably, and that is the original patent for the cooler.
Most coolers still have this problem where they don't keep ice cold for longer, for maybe a few hours, and that's it. There's been innovations, there's been new coolers that have been existing out there, but they still have the exact same problem that they still have not been able to solve.
And so we looked at similar solutions attempted in the past, and this first one had an input interface where you could plug in a solar panel or some type of power source, and refrigerant lines surrounding the walls. The second one was a picnic basket style design with a fold-out solar panel so you could increase the amount of power you could produce. And the third design used a thermosiphon to pull out the hot air and a fan and a heat sink to disperse that energy. The fourth design was an all-in-one with a solar panel built into the lid and coolant lines lining the bottom. And the fifth design was essentially a bag with gel packs that you would freeze and use it as a cooler. And so we put this into a similar solution matrix with certain parameters and figured out which design was best and what we could take from each design.
Before we built our cooler, the four main things that we came up with that were really important to us was our cooling technology, how food safe it was, how affordable it was, and then our power sources.
And the way we came up with that previous image was through this mind map where we sat down and brainstormed what we really wanted to achieve. So within the cooling technology, we really wanted to make sure that it extended the lifetime of ice by keeping the ice cold, and that our machinery was silent or quiet. We wanted to make sure that our power source was sustainable and easy to use, so we chose solar power. We added an additional category at the bottom of size because we wanted to make sure that this cooler was a similar size and weight to other coolers and that it would fit in any car. Within food safety, we wanted to make sure that it prevented spoilage by isolating the food and keeping it under that 40 degrees. And within affordability, both for us building it and for the consumers, we wanted to keep everything within $150 to $200.
Before we actually built our cooler, we sent out an initial survey to get some feedback from the consumers. We wanted to send this out, and we ended up sending it out all on social media with help of grandparents and just help of parents in general. We asked how long to use their current cooler that they own in succession, which out of the 550 responses we got on this survey, 62.4% said they use their current cooler one day / for day trips.
And we asked them if they would upgrade to a solar-powered or battery-powered cooler, and almost 60% of people said that they would.
We also asked how much they would be willing to spend on this cooler, and the highest category with 36% was actually $75 to $150. So we ended up lowering our price goal to keep our price for the consumers ideally would be under $150.
And so after brainstorming, we came up with a project solution that would use evaporative cooling techniques as well as a solar panel to keep ice frozen for longer and recover quicker when opening and closing.
Some criteria that we used to limit our design was we wanted to keep our weight under a certain limit so it didn't weigh much more than any cooler people currently own. The availability of supplies was a big limit to us because as just high school students, we don't have access to manufacturing machinery or technology or any sort of supplies like that. Affordability was a limit for us because as high schoolers, we're on a tight budget. We don't have a lot of money to spend on some high quality supplies. And we limited ourselves with food safety to make sure that this absolutely was food safe for all consumers. We don't want anyone getting sick. And our power source, we wanted to make sure it was sustainable.
We also had some parameters and some testable features that we wanted to do. The main two that we focused on was the ambient temperature and the change in temperature over time. We also got a control cooler that's the exact same cooler as that cooler that we ended up comparing to. And we also wanted to test the speed of ice melt and watch the difference between the coolers. And we also
And so the STEM concepts that we mainly use for this project include thermodynamics, circuitry, materials, and dimensioning to make sure everything could fit in the cooler and be safe for everybody to use.
So these are the sketches that we ended up coming up with. This one has a built-in solar panel on top that's connected to the fan, and that fan, as it's sucking in the air, it goes through a cold, wet sponge. This design kind of has the exact same system, but it's the detachable solar panel with the exact same sponge and fan system. This one actually has a pump where it has a reservoir in the bottom where that water is pumped up into that sponge, that fan sucking in the cold air, and this one has the exact same type of feel, except that the holes are not only on the floor, but it's also all around the walls where that air is being pushed into the cooler. And then our final design that we ended up coming up with, this one has a pump, exact same type of system, detachable solar panel. We ended up actually getting rid of our pump design because we realized it was impractical, and we realized that we didn't have the materials or the ability to actually get a pump and be able to build it with that.
So we ranked all of those sketches that we just showed you in a design matrix based on their cooling solution, battery placement, component protection, volume, weight, and cleaning ability, and took the best from each and decided that we needed to use a cooler with evaporative cooling techniques and that was gravity assisted with no pump.
And so for our final sketch, we had a fan, and we had the ice melt and the water run off into a sponge that would be down here, and a fan blowing air through the sponge so it would circulate throughout the entire system. And it had channels in the wall and the floor.
This is our 3D model that we built on Inventor. It comes with our isometric right, front, and top view. We decided to actually build our project in an existing cooler because we knew it would be a lot more sturdy, and instead of building the cooler out of styrofoam, we knew that the plastic casing would be a lot better. And we also wanted to be able to compare it to a control cooler of the exact same dimensions.
Here's some cutout views of the inside of our 3D model. This right side view shows these divots that we cut out from water drainage. This is our main food storage area and a ramp. And then this third picture is underneath the floor where our airflow channels are.
And for the 3D model of the solar box, the 2 solar panels go right here, as you can see over there. And all the circuitry goes inside the box where you then snap fit it closed, and it will not open again. And these are the 3D drawings of our components of this project. They're on page 30 of the portfolio if you would like to look at them closer.
We had multiple tools while building this cooler. We used an X-Acto knife to cut out our bigger pieces of styrofoam, including our floor, our walls, and any of our vertical walls. We also used Loctite all-purpose adhesive to glue all of our styrofoam pieces together and glue the styrofoam to the actual plastic of the walls because we knew it would actually be able to hold its sturdiness.
We also used a Kelvin wire foam cutter to get more precise cuts on the styrofoam for the smaller pieces such as the supports, and to cut out our sponge down to the size we needed it to. And we used a precision drill to drill drainage holes in the bottom of the cooler.
And Ms. Parker was nice enough to let us use her 3D printer to make the housing for the circuits, as well as her soldering iron, her wire strippers and cutters, and a multimeter to complete the circuit.
The first thing we did when we were constructing the cooler that we built was decide if we wanted a single or double layer floor of our styrofoam. So we cut out a single layer floor and a double layer floor and glued them together and tried to break them. As you can see in the picture on the right, the double layer floor was much more sturdy, and so our floor in our cooler was a double layer of 1/2-inch styrofoam so that it would be able to hold more weight and more food.
After we figured that out, we started actually building in the cooler. The picture on the left is how we decided to build the supports in the cooler. We wanted to dry it out before we actually started gluing stuff down. The picture on the right is after we started gluing all the styrofoam pieces down. It ranged from 1 inch to 1.5 inch as you went up. And then we also stuck skewers into the styrofoam to make it more sturdy when that floor actually got sat down on there. And we also covered it with a thin layer of shellac so it would be waterproof so that water couldn't get actually into the styrofoam itself.
The next thing we did was install styrofoam cubes and attach Velcro to them on the wall of the cooler and attach Velcro to the fan so that we could mount it there and it would be removable. That's in the picture on the left. In the center picture, you can see the sponge we cut down to the correct size and the box we built to support our small ramp. And in the third picture, you can see the small ramp installed and how the water from that drains directly into that sponge.
We did actually add initial supports for the floor. We ended up making more supports on the floor so then that once we installed the floor, that ramp would actually be tilted so that water would actually start flowing down. The picture on the right is how that fan was actually mounted in the cooler and how we ended up putting that all in there.
Next, we installed our floor, we glued that straight on top of the supports, our double layer floor. We constructed a new one after we tried to break the previous one. And then we installed walls, and those channels you can see in the side of the original cooler we used as our airflow channels, and that's how air circulated. We also installed the vertical wall that you can see in the picture on the right to help direct airflow towards the sponge.
After we installed that vertical wall, we actually made 2 more vertical walls. We needed walls basically where all that water was flowing out onto that rim or that sponge. The picture on the left is how we ended up cutting those divots, so no matter where the water actually went, it was forced into one central area, either onto the left or the right side. This is also our finished design. The small rim is on this side where it's tilting this way. Our fan's mounted on the wall, and then our sponge is down here, and underneath all of the floor is those channels.
And because we did add that category of size and wanting to make sure that this would fit in any car, my friend Amy let us borrow her tiny smart car for this picture, so you can see that this cooler does in fact fit in any size car.
And for the solar box build, there were 2 separate solar panels that ran at 5 volts and 250 milliamps. So we decided to wire them in parallel to increase the current so the battery would charge faster. And these are the 2 solar panels. And we used a 10 watt-hour battery to supply power when the solar panels could not, and a charging board so it could charge the battery and the fan at the same time.
This is our bill of materials. It shows our vendors, manufacturer, the items, and how much each of those items actually cost. As you can see, we have 2 coolers, styrofoam fan, we have the Velcro on there. Anything we ended up buying for this project we put on there, and it cost us $173.43 out of all of our materials.
We also put together an estimated manufacturing cost to detail how much this cooler would cost if we only purchased the exact supplies needed. And so this is closer to what it would be if it were mass produced. So things like our control cooler and the rest of our styrofoam that we didn't end up using are not included in this list.
And if it were mass produced, it would be much cheaper, more durable, and would have a lot more room inside of it, as well as perform better.
So the way that our cooler works is, this is our food storage area, this is our cutout beef earlier. And as your food is sitting in this area with the ice in it, as the ice melts, it drains this direction. It falls through our divots onto our sponge, or through the divots onto the rim onto the sponge, and then the fan forces air through the sponge, and that cold water in the sponge cools the air off, and then that air travels under the floor and up, circulating around the food.
We do multiple tests on this cooler. Our very first test, we wanted to measure the temperature in our cooler as well as the control cooler, using gully temperature sensors, and then using the computers that we had in the lab.
Our second test was to test for the lifetime of ice and keeping food cold, and the way that we did that was by freezing cups of like water and fruit, and freezing them and placing them in each cooler, our cooler and a control, along with ice. And we left the lids open so that we could see what was happening in there, but we added saran wrap on top so that there was still an element of insulation and air circulation, and we set up a time lapse to check on those.
And for the third test, we wanted to see if the solar panel could charge the battery with the fan running, and if the battery had enough capacity to run the fan through the night without extra charge for the solar panel.
So test results from test 1, we ended up running this test for 22 hours overnight, and the control cooler is that blue line, our cooler is the red line. Overall, our cooler was always colder. It did warm up around the same time, and then we did find out, which you can't really see unless you got on the computer and zoomed in, once we opened up that cooler and we closed it back, our temperature of our cooler jumped way quicker than the actual cooler itself, and it was able to recover a lot faster.
Our results for test 2, we ran this test for 8 hours, and at the end of those 8 hours, our build had a lot more ice and a lot less melted ice and water. No water had drained out yet. The other cooler was mostly water. All of the cups of fruit were still partially frozen, but ours were mostly frozen, the other ones were mostly melted.
And for test 3, the solar panels were able to fully charge the battery with the fan running, and was able to last 8 hours, which is enough to make it through the night, and matches up with our math, with it being a 10 watt-hour battery and a 5-volt fan at 250 milliamps.
After we built our cooler, we wanted to get it out to the public and see what people actually thought of it. We ended up sending it on social media. We made a YouTube video explaining everything. We also made a YouTube video of that trifold if you would like to get more look at it. We ended up getting 301 responses in total, which 92.7% ended up saying yes, they would buy this cooler, which was the very first question. We also had some responses when we went to Camping World, because they allowed us to come into their lobby and ask people in person, and they ended up giving
replace your current cooler? And 61% of people said that they would replace their current cooler, and 34% of people said that they would use ours and their current cooler.
96% of people said that they thought it was better than a regular cooler.
And then we also asked if they would even use our cooler, which almost 44% said that they would use it monthly, with 22.2% saying they would use it yearly.
This section is a little bit of a fun fact, but we asked customers what they would use it for, and the top categories were camping, short day trips, and picnics.
And we asked the participants of our survey to verify their age, so we knew our results weren't coming from a single demographic. And as you can see, it is evenly split among multiple age groups.
We also asked them if they would be willing to spend $150 on this cooler. Going back to our original survey, we wanted to make it underneath $150. So that was the whole reason we asked this question, which 82.1% said they would purchase this cooler for $150.
So all of that being said, there are some things that we wish we had done differently or would change if we were able to do this again, and would recommend to manufacturers if they were to manufacture this design. One thing is the drainage system. Currently, when the water drains after the sponge fills up, that water either flows over into our airflow area or drains out the bottom, just out of the cooler. And so ideally there would be another reservoir underneath the sponge that the water could drain into that could later be emptied with the spigot.
We do wish we could also change the materials. Obviously, styrofoam is not the best material because we had to cover it in shellac for waterproofing. We wish maybe we could use plastic or some other material to where we wouldn't have to do that extra step.
We also wish it was easier to clean. The way that we built it, there's no way to clean underneath where the airflow is, and so if water were to get in there, there's the issue of mildew occurring or mold, and so we wish we had made a way to open it and be able to clean it after each use.
And with the circuit, currently there's no way to charge the battery without using the solar panel, and there's no outlet USB. This would have been a good idea to have an inlet and output USB, so you could use it as a solar charger when needed, and you could charge the battery when you had access to power.
We do wish we could change the size of the cooler. Once we put everything in the cooler, the fan, the sponge, all of our styrofoam, we took down the actual food storage of the cooler, where basically it probably cut it in half. We wish that if we could have built things smaller, it wouldn't have taken that away from it.
And accessibility to the solar box itself is very limited because it was designed with snap fits. And what snap fits are these little hooks that you would put into something, and it would permanently close it, so it would be very hard to open it. But this is a very bad idea because if it got damaged, there would be no way to get into it and repair it without breaking the box itself. And we'd like to thank Ms. Parker for supporting us this entire year and answering our questions when we have them.
Special thanks to Camping World. They allowed us to go in their lobby, present to people, get real world experience, and then we got feedback from actual people on questions, and that kind of helped us kind of make what we wanted to change when we actually came up with that idea.
And also credit to SlidesGo, we downloaded our slideshow theme and font from their website. Thank you guys. We also have citations if anyone would like to see them.
Do we have any questions?